This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. So in the last lecture we discussed about channel length modulation. So what do you mean by channel length modulation? So when we look at the operating principle of MOS transistor, what we have noted is the electron concentration here is not actually uniform across the channel. This is a NMOS. In the case of NMOS, the majority carriers are the substrate got holes, but you get a channel made of electrons. So in the NMOS, the channel is made of electrons, and then the electron concentration is not uniform. And then what will happen is in the saturation region, you will be getting a pinch off, because in the saturation region, your VDS is greater than VGS minus VTH. So that this region, you don't have any channel. But then when you bias it here, you will see the moving electrons, but you don't see any accumulation here because you don't have that voltage to accumulate electrons here. But then this issue here, because you don't have electrons here in this channel, your actual channel length, here it is L, but then here your channel length reduced to L1. So your channel length actually reduced, actual channel length. So the channel length we measure in terms of the electron density, because electron density is from here it is high and then here it is kind of zero, and then the accumulated channel electron density. So that is the reason we say this is the length of the channel. When you have pinch off, your channel is reduced by delta L, but then still you get the current. As I discussed in the previous lecture, you get the current. Why? Because you got a very high electric field here because of the nanometer spacing. You get a very high electric field here, because here you got a voltage, here you got a voltage, here there is a voltage difference, that is V, and then the electric field is V by D. D is in the order of nanometers, so you get a very high electric field that will attract the electrons and then you get the current flowing. So when you take into account the channel length modulation, what will happen is your drain current will increase slightly. Like in the case of transistor, when you have early effect, then you got a slight increase in the drain current with respect to VDS. For the BJT, collector current slightly increased with respect to VCE. So that was due to early effect, but then this increment is due to channel length modulation. So when we say we don't have any channel length modulation, means then this is a straight line, dotted line. We don't have any channel length modulation. But then when you have channel length modulation, you can see there is a slight increment, means when you have pinch off. Then in the actual case, we have pinch off in the case of MOS transistors, so that we don't get this dotted line. We get a small slope. Then we modify the equation. So this is the equation for the drain current when we don't take into account the channel length modulation. So ID equal to 1 by 2 mu n, mobility of electrons, capacitance per unit length COX, width of the gate, length of the channel L, and VGS minus VTH the whole square. So this is the equation without channel length modulation. When you take into account the channel length modulation, you have to add 1 plus lambda into VDS. So that is a term we will be adding to take into account this effect, this slight increment, and then lambda is the channel length modulation actually. Lambda is called channel length modulation. The original observation that the current is constant in the saturation region is not quite correct, means this straight line. The end point of the channel actually moves towards the source. See, the channel actually moves towards the source region. It's not here, it is moving towards the source region. As the VD increases, means this VD increases, increasing ID. So your ID is actually increasing. Therefore, the current in the saturation region is a weak function of the drain voltage. And then we take into account the channel length modulation, then we got this slight increment. So this channel length modulation is equivalent of Early effect in the case of BJT. Lambda and L. So lambda is the channel length modulation, L is the length of the channel. So ID lambda, if you take into account the channel length modulation, you write here ID subscript D and lambda. If you see D lambda means then we are taking into account the channel length modulation, then our equation to have an extra term that is 1 plus lambda VDS. Then lambda VDS, that is equal to delta L by L. So you can see. So if your delta L equal to 0, means you don't have any pinch off. If your delta L equal to 0, you can see here you don't have the pinch off. If delta L equal to 0, then your lambda equal to 0, so you don't have this term. And then this is a channel length modulation. But then now we are going to compare. Unlike the early voltage in BJT, the channel length modulation factor can be controlled by circuit designer. So what do you mean by controlling by a circuit designer? Yeah, so one more thing. So this graph also I want to show you. So in this graph what I want to show you is see lambda is the channel length modulation. So if you got a more channel length modulation means your delta L by L. So what will happen if your L is increasing for a given VDS? So if your L is increasing, what will happen? Your channel length modulation will decrease because this is in the denominator. So that is the reason channel length modulation decreases means then you don't have that very high output impedance. See, the RO is reducing. When L is very small, then actually the slope will be very high because the channel length modulation is increasing. Then lambda VDS equal to delta L by L. Then that is expression. Then my question is, what is the expression for early voltage? VA, what is the expression? Because you have done it in the lab as well. Or what is the expression for RO? Sorry, VA divided by? Yes, for the early effect. So maybe RO, first you have to find out because then only we can make a comparison. Then only you can understand what I have written here. So what is expression for RO? So V equal to I into R. From this you can immediately write. So VA divided by IC. That is output impedance with early effect. So that's the reason you are getting, this is your VCE and then this is your IC. So that you are getting like an increment. And then this slope, 1 by slope is the RO. This will decide. So if you don't take into account early effect, VA equal to infinity, RO equal to infinity. But then you see here, then early voltage, that VA, that is equal to what is early voltage? RO into IC. So the early voltage, then you can see here RO into IC. So this is the output impedance. Then you are getting the collector current. So maybe I can write RO IS exponential BB by BT for the case of BJT because IC is controlled by the BBE. And then if you look at this one, how will you control it? So can a designer control it? because there is a very difficult for a designer to control the early voltage. Why? Because the VB, actually it is very difficult to understand how much it is modulating. If you recall the early effect in the case of BJT, what is happening is you got the PN junction here. So you got the PN junction, then what is happening is here you got the narrow base region. So here is the, this is the base, this is the collector, and then this is the emitter, heavily doped, N plus, and then NP. But then here you are getting the junction, see, and then when you apply more voltage here, so what is happening is, so this is your VBE. So if you recall early effect, why we are getting early effect? Because when you increase this voltage, this width is decreasing here, because this reverse bias will increase from here to here, and then you are getting a less width, and then the electrons coming here will recombine with only less number of holes. That's the reason your collector current is increasing, which we already discussed. But the problem is we don't know how much it is increasing. We can't see. It is inside the semiconductor. So actually you don't have the control because we don't know. But in the case of channel length modulation, the good news is here if you look at the equation, lambda equal to VDS delta L by L. So if by varying L, actually you can directly control the channel length modulation. Because L, who is deciding L? Length of the channel, you are designing. The designer is going to choose what is the length I wanted between source and drain, which you can design properly. But then the early effect that is happening inside the PN junction, the width is increasing, but we don't know how much it is increasing. You can't decide, you know what I meant? So in a particular fabrication, I am going to fabricate thousands of transistors in a particular fabrication setting. Then my 1000 will get one early effect. But when I put in another slot, then when I vary a little bit in the process, then I will get another early effect. You know what I meant? Why? Because the designer, I can't put in anything. It is decided by how the junction is formed. Because you take a P and then you take a N type and then you join together, and then you have only a limited control how much width you are getting inside the depletion region. You can, you know, somehow you can control it, but you can't accurately control. So because of that, in a given slot, in a given fabrication setting, given slot, when you are fabricating BJT, you get one early voltage. But when you vary this again setting, you try to make same setting, still you get a slight different early voltage. That is because the early voltage here you can see that is happening because of this width is here varying when you increase this voltage, and then we don't know how much it is varying. We can't see we can't measure it accurately. But then here, channel length modulation is quite simple equation, VDS equal to delta L by L, and then you can increase. So my question is, this is an example. You guys are working in BJT company, you are working in channel length, you know, most transistor company, and then I come in and say, oh yeah, I want to increase the early effect. Can you increase it? Yeah, you may have some technique, but then I will say some precise value, I want to increase this much. Then you will struggle. You know, you can increase early effect definitely, but then I will say my requirement is this much. Can you precisely control? Who will be controlling? Then none of you will say I can control because you don't have the parameter to control. But the most transistor people will say how much you want? Yeah, this much. Then I will control the length of the channel, and then you can control it. So that's what it said. Unlike early voltage in BJT, the channel length modulation factor can be controlled by the circuit engineer. That is the reason in the modern technology, your L is very, very small because L is the process technology. Now we have got, I think, 12 nanometer technology. So you got a more channel length modulation. Then base, see I have written here, base width of bipolar devices cannot be adjusted by the circuit engineer. So that's the main problem, base width. Hence, constant early voltage for all transistors in a given technology. See, that's the problem. For long L, the channel length modulation effect is less than that of short L. So that's what I have shown. So then this, why I have shown is I have deliberately put this graph. Why? Because now your process technology is reducing, like 28 nanometer in 2014. Now you have got 12 nanometer technology. Then in 2019, this is 2019, maybe 2020 you are going to get maybe 8 nanometer technology or 7 nanometer technology. Then this L is actually the length of the channel. This is called the process technology. So when your process technology is reducing, coming down, then what your channel length modulation is actually increasing. Then transconductance. Similar to BJT, we have transconductance for most transistor, which is equal to, for the BJT that was GM equal to, what was the transconductance? IC by VBE, because output current divided by input voltage. For most simple output current, that is drain current, divided by not VBE, VGS, between gate and source. Transconductance is a measure of how strong drain current changes when the gate voltage changes. Similar to BJT, transconductance is a measure of how strong the collector current changes when your base emitter voltage is changed. Same thing. Then, if you are not taking into account channel length modulation, ID equal to 1 by 2 mu n COX W by L VGS minus VTH the whole square. This is expression. Then we can find out transconductance. How will you find out transconductance? You can just see delta ID by delta VGS. If you just differentiate, then you can get expression for transconductance, because this is the only time you are differentiating. So if you delta ID by delta VGS, when you do, this will become 2 times VGS minus VTH into delta VGS by delta VGS. So that is the reason you are getting this expression. Then in this expression, GM, transconductance, half mu n COX W by L 2 into VGS minus VTH. Maybe I can substitute VGS minus VTH from here. So that is, then I can get an expression in terms of ID. So that's what I'm getting. See, I got different expression for GM. So what I'm doing is, this is the expression when you differentiate this delta ID by delta VGS. When you differentiate this ID with respect to VGS, what you are getting is this one. But then I can substitute VGS minus VTH. Maybe I can find out from here, which is equal to 2ID divided by mu n COX into L by W the square root. So then I can substitute here. So then I can write down GM in different forms. Mu n COX W by L VGS minus VTH. Or GM equal to root of 2 into mu n COX W by L into ID. Depending upon which part you are substituting. So because GM you got this much, then you can substitute a different way. See, half mu n COX W by L. See, half mu n CX W by L. So then I can substitute instead of that ID by VG minus VTH the whole square. Then what will happen? You get this expression. You know what I meant? So in this one, from this equation, you can substitute in different ways and you can get different GM values. Then the question is, which GM is correct? So then all the GMs are technically correct, but then when you have a problem, maybe you can look at which one is given, then choose a GM accordingly. Then if you, again people ask, no, I am not happy with that one, which one is more accurate? The GM should have some VGS dependence. Then only that expression is correct. But when you check here, all got, because here you got VGS, and then here you got ID, again ID got VGS, then GM which is equal to 2ID by VGS minus VTH. See? So in the problem, then how will you choose? If you don't know mu n, if you don't know COX, nothing is given, then you can maybe use this expression. You don't need any of these. So that is you can find out from the problem. So just for solving the problem. So this is a actual expression for transconductance. So this 2 will cancel out. Mu n COX W by L VGS minus VTH. This is a standard equation. But then we can modify. The advantage of modification is you can keep W by L constant. Then VGS minus VTH variable. Or you can make W by L variable or VGS minus VTH constant. Different things you can vary to vary the transconductance. So if you keep W by L constant and then VGS minus VTH variable, then what will happen? W by L constant, VGS minus VTH variable. So which expression is correct then? So you are keeping W by L constant. Then you are going to vary VGS minus VTH. So you get GM, then in that case you can see GM proportional to delta ID. So where is the delta ID? So this is the expression. So W by L you are constant, and then you are varying VGS minus VTH. Then your GM is proportional to delta ID. And then from this expression, if you keep this one constant, you can also write GM proportional to VGS minus VTH. So these are the different ways of writing GM, and then you can vary differently. Like you can keep either W by L constant or you vary VGS minus VTH constant to change the GM. So the meaning is GM can be varied in different ways. So W by L constant means when you design, you already fixed width and length, channel length. Then if you want to change your GM, then you have only option change the VGS. But then if VGS is already given in your circuit, people say that, okay, this is our threshold value, this is a VGS we are supplying, and then for getting a particular transconductance, then you, in the design, you can vary the width and length of the channel. Usually people vary the width. So doubling of GM due to doubling of W by L and ID. So GM, which is equal to different expressions we can take. One expression is square root mu and COX W by L into ID. And then what will happen is you can double the GM. If you want to double the GM, what will happen? What you have to do? So you can double W by L and then you can double ID. So if you are doubling, then your GM, because this become 2 times, this become 2 times 4, then it will come out as a 2 and then you can double it. If W by L and ID are doubled, effectively 2 equivalent transistors are added in parallel, thus doubling GM. So you can double the GM if you connect 2 transistors in parallel. Then there is also sometimes people write in this one we don't have to study body effect, but still I thought I will use this slide so that, because sometimes you will see people write MOS and then they put a ground from here, you might have seen. And then I want to show you, because what is that symbol? Most of them, the realistic circuit, they put from here, then you can see a dotted symbol to the ground. Sometimes they connect some voltage here. Then you should not be getting confused, because you studied MOS transistor, PMOS, NMOS, but then you see some new notation, then you might be thinking what these guys are doing. So that what they are doing is they will ground sometimes a substrate. So that's what is shown. Here means earlier it was floating. In the real design, when you design the chip, they will ground this P substrate. So when you ground this P substrate, so this is a NMOS. And then when you ground it, see P region you have grounded. N region again you have grounded. So you are getting a, because this is a PN junction, and then you got a depletion region. If you want to get rid of this depletion region, you have to connect P positive and then N negative. But then this one is anyway negative ground. But then because you connected this also to the ground, then you get a depletion region here. So that is the reason. In the real design, they will connect something like this in the notation. So when you see this notation, you have to understand in the MOS, the body is grounded. That is a symbol. That what you have to understand is. Then sometimes people also connect some voltage here, some negative voltage. Why? Because they may want to control the width of this depletion region for some reason. Because when you control this width, you are also controlling the width of the channel here. Not this width, the height here. The height you can control a little bit. So then in that case, if they are doing like that, because here you can see more negative is connected, so that you are, this is becoming more negative, reverse biased. So in that case, then people will write, maybe here they will write it as a negative. Then when you have this body effect, when you take into account body effect, means because of this body you are grounding or you are negative you are connecting, then people will ask what is effect? What we have to look into it? Because when you see this notation, and then in another one without notation, then you might ask, why do we need to ground it? So we need to ground the substrate in the design. Definitely we can't leave it floating. There will be maybe some leakage current. So in the design, original chip design, they will ground it. Then the question is, when you ground it, people might ask in the foundry, then what is the effect? We are grounding the body, and then is there any effect? Then definitely there is an effect. People already found out your threshold voltage will increase slightly. If you don't have this, if you leave it floating, then your VTH equal to VTH0. That is a value. But if you are going for body effect, if you take into account body effect, then you need some additional term plus gamma, then some 2 root phi f plus VSB minus 2 phi f. So then just I am showing VTH is a threshold voltage and VSB equal to 0 means in the case of previous case. And then gamma and phi f are technology dependent parameters having typical values of around 0.4 delta V, the voltage, and 0.4 volt respectively. I have just shown you, these parameters. Then the thing what you have to understand is when you ground your substrate, that is called, you have to take into account the body effect. In the real design, definitely this will be grounded. and or sometimes the people connect to some different voltages, but most of the time it will be grounded. So when you ground it, the effect is it will increase the threshold voltage, that's all. And then these parameters are, they may have got from experimentally, the range, they measured it. So then now we are going to, now we know the MOS, how MOS is amplifying the signal. Yeah, maybe that is another aspect you should be thinking. So the BJT, we know how it is amplifying. So how about a MOS? How about a MOS is amplifying the signal? How MOS is amplifying your signal? So that is my coffee question 2. So my coffee question 1 was related to BJT. So my coffee question 2 is, so you can email me how MOS is amplifying your, what MOS is amplifying? What BJT is amplifying?
Amplifying your base current.
Yeah, so you can say, yeah, BJT is a voltage controlled current source, and then IB is amplifying. Yeah, maybe I got 2 questions for MOS. The first one is whether MOS is a voltage controlled current source or current controlled current source. You know, BJT everybody knows it's a voltage controlled current source. So my question is MOS, whether it is a voltage controlled current source, current controlled current source, or voltage controlled voltage source. Okay, that is a question number 1. You can just write, oh, this is voltage controlled voltage source, whatever the result. Then the second question is, how will you explain amplification in MOS transistor? Because in MOS transistor there is a tricky part, because in the BJT, maybe I'll give you this some clue, so that you have to give me half cup of coffee. I'll buy you coffee, but then you have to give me half now. So you get only half cup of coffee. Yeah, so then the BJT, the thing is, you know that the IB is going from here and then it is going to the collector. But then when it comes to MOS, that's what I want you to be thinking. And then the MOS, this is a metal, then you got the dielectric oxide, then you are going to get source, then you are going to get drain, and then this is your substrate. And then here is your channel, this is your gate, and then this I have connected. Then here I want to see how you are going to explain amplification. Why? Because when you have connect your gate here, what is the current between gate and source? Yeah, 0. So your current between gate and source is 0. Then how will you explain me the amplification? Because for BJT it was easy. BJT, you know that from here you got a voltage, then what is happening is you are injecting maybe 10 holes to this region, 10 holes came here, then because this is heavily doped, maybe 1000 electrons came to this region, maybe 10 recombine with P region, remaining 900 seep through, and then you got it. So you got amplification. Then you can write IC by IB, that is my gain. But then somebody might ask, how will you explain, the amplification? So so you have to explain then the current, how current is amplifying, or how will you explain? Somebody will ask, okay, BJT I know, this is where you can explain, but MOS, how will you do? So this is the only 2 questions. So email me, and so maybe first 5 entries, I will first 5 correct answers I will pick up. Yeah, then that part is over, the fundamental aspect. And then the large signal models. When we studied BJT, we discussed actually large signal model first, then we studied small signal. In the case of MOS, again, we don't have to study large signal models in detail, but then we will be studying small signal models. In the MOS, if you are operating in the saturation region, saturation is a useful region in the amplifier. Saturation region, then VGS is greater than VTH, your VDS is greater than VGS minus VTH. Then only you get your MOS operating in this region. And then this current is half mu n COX W by L VGS minus VTH the whole square. And then here I put it open. Why? Yeah, because there is no current is flowing between gate and source, and the impedance equal to infinity, because then you can find out V equal to I into R, R equal to V by I equal to 0. So that's infinity. So when you have infinite resistance means we keep it open. So in the MOS R pi, you can put it infinity. So what is the difference between BJT and MOS when it comes to small signal? The only difference is you put R pi equal to infinity, then you get to the MOS small signal model. But obviously this current is different for IC, but in the just drawing, that is the only difference. So this is in the triode region, this is expression which we already got derived this expression. Deep triode region means further into the linear region. So triode region is the entire from here, from this dotted line to the left, this entire region is triode. But the deep triode region is somewhere here, the ohmic region. So that is the reason then you can use your MOS transistor as a voltage controlled resistance. And we derived this expression in the last lecture. Now we are going to find out the small signal. So that is our interest. So for the MOS, this is a small signal. So you have got gate, that is a gate. Then you got source, this is got a drain. Then you can say that your current, that is equal to GM into VGS. Pretty much like GM into VBE. So here it is GM into VGS. So if you are taking into account the channel length modulation, now you will not use the early effect, the channel length modulation. If you are taking into account the channel length modulation, we will be putting RO. And then this is the RO, that is the reason we are getting the slope, which is equal to delta ID by delta VDS, the whole raised to -1. You can easily derive it, because if this is the expression for the current which we already got it, ID lambda, and with the channel length modulation, you are getting 1 plus lambda into VDS. Then you can just differentiate. So when you differentiate is delta ID by delta VDS, and then when you differentiate it, what will happen is this expression, see, then you are getting by 1 by lambda, and then you will be getting 1 by 2 mu n COX W by L VGS minus VTH the whole square and lambda, just differentiating, so nothing else. Then for this one, I can substitute as ID without early effect. So then I can say that RO approximately equal to 1 by lambda times ID. When the bias point is not perturbed significantly, small signal model can be used to facilitate calculation. Since we already said a large signal model and a small signal model. Large signal model means when you connect some input signal, if you are disturbing the VC for the BJT, if that is fluctuating the DC bias conditions, then it is in the large signal model. Same concept in the case of MOS transistor. If you are varying the drain voltage a lot when you connect your input signal, then you are operating in the small signal. But if your bias point is not perturbed significantly when you connect your signal, then you can say that is in the small signal region. To represent the channel length modulation, an output resistance is inserted into the model, which we already know. For BJT, we inserted RO when we taking into account early effect. Then we have to look into PMOS transistor. So PMOS transistor means NMOS, we studied NMOS. In the PMOS transistor, then we will be fabricating on the N substrate. NMOS transistor we fabricate on the P substrate. And then the PMOS is equivalent part for PNP transistor. And then in the PMOS, this is N substrate. Then we will be having P plus and then P plus region, and then we have got gate. And then this is the representation. Gate, drain, source, then the arrow to the inward. So to show that this is the direction of the current. Then a question for you. For PMOS transistor, the channel is made of electrons or holes. Yeah, for the PMOS transistor, we are taking N substrate, and then the channel should be made of holes. But if channel is made of holes, what should be the gate voltage? Yeah, because you have to connect negative voltage, because when you connect negative voltage, then this part will be negative. And then this is N substrate. Majority of carriers are electrons here. So many electrons will be here, free electrons. And then when you connect a negative charge here, that electrons will be repelled down initially. And then you get a depletion region here initially. But then when you increase this negative charge, what will happen is holes will come out from here and then here mainly. And then also some from here. Here you got a minority, but not much. And mainly this will come from these two regions, and then you get a channel made of holes in the end substrate. So that is the PMOS. Then the PMOS is operating, normally. Then suppose you connect a positive charge here for the PMOS, what will happen? So if you connect a positive charge here, see, you got positive charge, positive charge, positive charge, then what will happen? This will attract the electrons here. So will it operate or not?
They recombine within the positive substrate. If you apply voltage.
So here you have connected positive charge, then what will happen is then obviously it should be negative charge, the electrons should be attracting. That's my question. So you have to think about it and let me know in the next lecture. Because otherwise people will ask, okay, you know the channel formation, you have to critically think. First you have to ask question to yourself, okay, then what will happen, if I connect a positive charge? Because you already agreed, when I connect negative charge, definitely you are getting a channel. Then my question is, what will happen if I connect positive charge? Then same way for N, so then you will say, oh, PMOS, I don't like PMOS. Then how about NMOS? NMOS, if I connect negative charge, what will happen? Have you thought of it?
There are already it's an end substrate, so there are already the electrons there, sir, in that region. So there won't be any chance because the majority charge carrier will be, for this case, electrons.
Okay, so he partially answered, then there can't be a channel formation because channel means you are making a channel. You know what I meant?
There's a difference. There are already electrons there anyways because majority charge carriers will be electrons there. So even if you are forming a channel, it will be a combination of only negative ions. There won't be any charge separation within the substrate.
Yeah. So he already partially answered the question, but still please think about it. Rest of you guys think about it and let me know in the next lecture. So PMOS transistor for NMOS, so we will compare between CMOS and NMOS. So N channel MOSFET is called NMOS because N channel, N is coming because you are getting negative electrons, negative for NMOS. For PMOS, positive means your channel is made of holes. For NMOS transistor, cutoff region means if your VGS is less than the threshold voltage, then your transistor is anyway off, cutoff region. Then you can operate your transistor, NMOS transistor in the linear region or triode region if your VGS is greater than VT, threshold voltage. Then again you got one more. When this is correct, when your transistor is on, then people will ask the next question, whether it is in the triode region or saturation region. So if this is the case, VDS, you find out VDS, voltage at drain minus voltage at source, which is less than or equal to VGS minus VT, then that is in the linear region. Then VGS minus VTH, that is on, transistor is on. If it is VDS greater than VGS minus VTH, then it is in the saturation region. So when it comes to PMOS, some students may mistake. Why? Because in the case of PMOS, the threshold voltage is negative because here you will be connecting negative voltage, Then better you take VSG less than the modulus of this value. So you don't have to take into account the negative. So this is the maybe best way to solve the equation. So don't take into account the negative. So just check VSG, just check VSG because voltage between source and the gate, Vs minus Vg, that is less than Vt, modulus of Vt, then it is cutoff region. In order to on your transistor PMOS, you have to make sure that voltage at between S and G, Vs minus Vg, voltage at source minus voltage at gate should be greater than modulus of the threshold. And then it is in the linear region if voltage at the source minus voltage at drain less than voltage at source gate, VSG minus modulus of this Vt. So the only difference is you just, this will be inverted like GS will become SG. In the case of BJT also we know that VB and then VB and then for PNP it is VEB. Same way. Saturation, VSG greater than modulus of this value and then VSD should be greater than VSG minus modulus of VT. Just like a PNP transistor in bipolar technology, it is possible to create a MOS device where holes are dominant carriers. So that's what we discussed here. It is called a PMOS transistor. It behaves like NMOS device with all the polarities reversed. So that's what I have shown here. And then this is an example triode region. In the triode region means your VTH means it should be greater than the threshold here. This is the drain voltage. So the drain voltage is here you got positive, here you got negative. Means you should have more negative here than it is in the drain. See, that's the reason. Then only you get this one. VSD should be greater than VSG minus VT. Edge of saturation, VSD equal to VSG minus VT means the modulus of VT. And then saturation region, VSD should be greater than VSG minus VT. So that's what I have shown here. So when we do a couple of problems, you will understand this. So PMOS equations. In the PMOS, the NMOS equations are equally valid for PMOS. So then for the PMOS, what we will write 1 by 2, then here mobility of electrons, here mobility of holes, because your channel is made of holes. Then capacitance per unit area, sorry, unit length, width, length. Then we will write VGS, not VS. So VGS minus VTH the whole square into 1 minus lambda into VDS. So when it comes to PMOS, what we will write is, we only will take the modulus VGS, see, modulus VTH. You can write like this as well. If you take the modulus, then you don't have to worry about the sign, because the threshold is negative and then VGS also is negative. So if you take this equation with the modulus, then you don't have to worry about the the sign, because the threshold is negative for PMOS. So like here. So when we do the problem, you will understand. So these are the equations. Then I think maybe we should go to the problem. Maybe before the problem, I would like to ask you this question. So small signal model, find impedance. So for this MOS transistor, what I did is you got a drain, gate, source, and then I put here is Rx. So my question is, how will you find out impedance when you look from here? So then you have to draw first you have to draw the small signal. So when you draw the small signal, it's just an example, because you already know small signal. Because if you are an expert in BJT, the MOS is very simple, because MOS you don't have R pi. So then what you have got is, here you got a MOS transistor. See, that is grounded. Then this is a gate, this is a source, and then the question is gate connected to the drain. So that's the interesting thing. So this is the drain, and then here the question is, what is Rx? So that's the question. So if you want to find out Rx, then gate connected to the drain. So you have to be careful. So then I will draw from here. So that is, that's what we do. That is a gate, and then input impedance infinity, so that I don't have anything. So source. And then here I can maybe put positive, negative, same way, if you put positive here, negative here, your current source it should be going down. So here I will put down the arrow, because here I put negative, positive, and then here I put negative. Then this is a drain. Then if I take into account channel length modulation, then I have to take into account RO. Then I got it here, so this is my drain. Then here the problem is, here is the Rx. So I am going to find out the impedance. Then if I want to find out the impedance, what is the rule? So if I want to find out impedance at Rx, that is output drain, so what is the rule? Yeah, so apply a test voltage source here, and then if your input is open, you ground it. You know what I meant? So apply a test voltage source and then ground the input if it is open. But here the input is not open, it is connected together. So please don't ground it, because this input, you don't have an input here, because input is already closed here. And then, so I am going to connect a test voltage source here. So that is a Vx, and then that is a Ix. Then drain and source connected. So see, I showed a drain and source connected. See, because this, drain and gate. See, drain is connected to gate. So if you look at from here, you check here gate, then you got infinite impedance, and then that is the reason open. Then source is grounded. Then you can put here positive, negative, or here negative, positive. I put here positive, here negative, and then so this is down, arrow is down. Then that is a drain. Then if you take into account early effect, you got arrow. Then in order to find out output impedance, we will be connecting a test voltage source Vx, and then what we will do is we pump Ix current, and then we short the input if the input is open. But here input is not open, your input is actually connected to the drain, so you don't have an open input, so you don't have to short it. So that is the reason the gate I connected directly to the drain. So this is the equation. Now we can find out what is Rx. So it's easy to find out Rx. So if this is Vx, then what is the voltage between these two? It should be Vx because it's coming in parallel. Then what is the voltage between this point and this point? Yeah, all are Vx because here all the line same voltage, and then this is the ground. Then I can write Ix. So Ix current is coming, and then what is the current? So this will split into two. Ix come here, one current will go here, another current will go, and then so this may be Ix. So this is the I1, this is the I2. So Ix equal to I1 plus I2, which is equal to what is I1? Yeah, because here you got Vx, and then this is ground. So Vx by Ro, that is your current through I1. So what is your I2? So I2 is coming, then here it is open, so nothing current can flow. So I2 will be your Gm into VGS. But what is VGS? Vx. So you already got Vx. Then it is ECC, you got Ix, which is equal to Vx into 1 by Ro plus Gm. So your Vx by Ix, which is your Rx, which is equal to what is 1 by Ro plus Gm, which is equal to what is this one? 1 by Gm parallel Ro. See, that's quite simple. Because here it's very simple. So if you write down Ix, which is equal to Vx by Ro, because here the voltage is Vx. See, this voltage is Vx, this voltage is Vx, plus I1 is passing through to the ground, and then here also this I2 it cannot go through here. So that is the reason for BJT you have to take into account this R pi, but then you don't have to take into account R pi here is infinity. So it is easy actually for MOS. MOS circuits are easy to analyze when it comes to small signal. Then you can find out Rx, which is equal to 1 by Ro plus Gm. 1 by Ro plus Gm is actually 1 by Gm parallel Ro. So then that we got it. So I have got the small signal here. Then another one is this circuit. So are they same or different? So one is NMOS, another one is definitely PMOS, because you can see the arrow is going in. And then my question is, so you can draw the small signal. I drew the small signal. Then what I did is I flipped it down so that it will be kind of looking like this. See, and then I have drew the small signal for you. When I draw the small signal, I'll be getting something like this. And then if I want to find out the output impedance Ry, then I have connected a test voltage source. And then again the input you don't have to ground it because you don't have any open input. And then you will be getting this one. And then my question is, will you please find out Ry? So I found out Rx for you. So why don't you please find out Ry and bring it in the next lecture. So you got two things for the next lecture. Actually three. Coffee question, please email me. So coffee question I can remind you again, two questions. Whether MOS is a voltage controlled voltage source, current controlled voltage source, or voltage controlled current source, please email me. And then how MOS is amplifying the signal. Then second one, that is a coffee question. The second question you should be thinking is what will happen if you connect a positive voltage to PMOS or a negative gate voltage to NMOS. The third question is you have to find out Ry, and please tell me compare with Rx. So I know that there are so many questions, I wouldn't be seeing many of you in the next lecture. If that is the case, I will skip the question and then we'll ask maybe in the next coming lecture. Okay, so I will stop here and continue in the next lecture. So please find out RY and then you can also email me.
Maybe there is another lecture here. So I put it here, this one I will take it. Yes, please come. Yeah, then I'll try to give her. Yes, please come.
Okay.